For center of mass, you have to pick a reference point, a place that you're going to base your measurement on, because center of mass is a place. So I chose this side, the left side, when I did it. But you can choose anywhere you want. Somebody chose 2 meters in. You can do that. That means that your location of your center of mass will be a distance from there. But if you're going to choose someplace in the middle, you have to remember center of mass is a vector, so you're going to have to make your distances positive and negative. And that'll work. I think it's easiest to pick one of the masses as your center of mass. That kind of wipes it out in the calculation and makes just doing the math a little bit easier. So if I choose here and make that 0, the center of mass formula is the mass times the distance from the reference point. For that first one, that's 5 times 0. And then I'm going to add to it the next mass times its distance from the reference point. That's 15 times 6. And then you divide by the total mass, which is 5 plus 15. And that gets you 90 over 20, which is 4.5 meters. If you did it from the other side, you got 1.5 meters. Total 6. So it's got to be somewhere in the middle. Now, any question about that? No, there should be. Good morning.
Morning.
I thought you had an ROTC thing today.
I did.
Okay. The next thing is to find the moment of inertia from the center. This doesn't require any of the stuff that's here. I'm sorry, at least it requires none of this. So if you're going to find the moment of inertia from the center, that's mr squared for each mass measured from the center. So this r equals 3, because that's from the center to where that mass is, 3 meters away. 5 times 3 squared. Now I have to do that for the next mass, which is 3 meters away, but it's 15 times 3 squared. mr squared, add them both together, and you get 180 kilogram meter squared. Any question about that? All right. This class had the largest number of people who, for question number 3, had written out motion variables. If you don't hear anything about velocities, times, or displacements, you can't use motion variables. So for an acceleration, when you're asked to find an acceleration, the place you should always start is net torque or net force. Then, if you can't use that, look for something else. And this is no different. Net torque equals I alpha. However, to do this, we had to identify torques that were here. And one of the things we had to do is realize that there's a torque from the 5 kilogram and a torque from the 15. And for every torque, R times F times the sine of the angle. We need an R, an F, and an angle. But also, you have to decide what direction each of these torques is. Are they in the same direction or are they in opposing directions? If you're spinning it about its middle, well, this one wants to go that way, and this one wants to go that way. So is out of the board positive or is into the board positive? You have to choose. I made into the board positive. That made this one positive, and it made this one negative. You could do clockwise and counterclockwise if it's better for you. The torque arm length is the 3. So 3 times 5 times 10 for mg times the sine of 90 degrees. That's the first mass one that's on the left. The next mass that's on the right, 3, 15 times 10 times sine 90 degrees. I believe this gives you 450 and negative 150. When we add those up, you get 300 meter newtons. Some of you got to 450 and 150 and didn't get 300 when you added them, when you subtracted them. I'm not going to call that person out, but they're probably feeling a little sad. Set that equal to I alpha. We just got I from over here. So 300 divided by 180 gives you alpha equals 1.7 radians per second squared. That was it. Any questions? Yep.
So at first, I fixed it after, but what was weird is I got that acceleration the first time, and for all the R
It's not coincidental. But what happens is, well, I'm sorry, coincidence is the wrong word. It's, if you put 6 in for all of them, then you made the torque on the left side twice as big, while at the same time making the torque on the right side twice as big. And you've also made the moments of inertia bigger, so you get the same acceleration. Does that make sense? All right, not terrible. I'm not gonna sweat this one too much. This is not what it's gonna be like on the AP exam. We're just trying to make sure we got these basics down. I'm doing this because somebody asked me about this. So I want to make sure that we're not complacent. I want to do one that has angles involved in it. So I'm going to choose a bar. So this is and again, I'm leaving the point mass thing for a minute. Let's say this bar is 3 meters long and has a mass of 20 kilograms. And let's say that it's free to pivot about its middle and is experiencing 1, 2, 3 forces. And I'm going to number them just like that. 1, 2, 3 forces. Let's say that force number 1, 20 newtons, and is at a right angle to the bar, and it's at the one end of the bar. Let's say force number 2 is 35 newtons, and it is 0.75 meters from the pivot point at an angle of 60 degrees. And let's say this last one is 30. Trying to make the arrows about the same size. I think maybe we'll go 40. 40 newtons at an angle of 45 degrees. Somebody had asked, what do we do if there's angles involved? I knew we hadn't done any like this. I would like this to be our question. I think you guys can probably do this problem with not too much effort, but I want to give you a whack at it anyways. It is a rigid bar rotated about its middle. I'm saying that pretty clearly because this is a net torque problem, and I am asking for the angular acceleration of the system. So is that clear? Can everybody see it from where they're sitting? I'm going to perform the problem in just a minute. I want you guys to give it a try. I'm just going to jot a few things down while you guys are working. Like, I think there are 3 torques. I'm gonna stop right here and say I calculated the net torque. I got 10.3 meter newtons. I found 3 individual torques. Torque number 1, which is located at the end of the rod, is a distance 1.5 away from the pivot point. It's a force of 20 newtons, sine of 90 degrees. Then torque number 2 is located a given distance of 0.75 meters from the pivot point. Size 35 newtons, sine 60 degrees. So that's this. I made both of those positive because they're causing the system to turn this way. So now I have one more torque. It's located 1.5 meters away. Size 40 newtons, sine 45 degrees. I made this one negative, which is causing the system to turn this way. We're trying to. So I tend to be explicit so that you guys can see all the parts. So 30, 22.7, 42.4. Made them positive and negative, add them together. Any questions there? So you're telling me if I came by and looked at everybody's paper, I'd see the right answer. Trying to make sure, because that's not what I saw in the quiz. All right. Just a brief observation. There's 2 of you in the room who did no writing over the last few minutes. So that causes me some concern. So I should be able to call those people out and ask them, what they did next. But I don't really want to do that. I'm trying not to exploit you. But if I'm asking for you to participate, you should be. Because there was something you had to do next. You had to look something up. I didn't give it to you. Did you look it up? Okay, so, Lily, what is the moment of inertia about the middle? That's it. So you need to find the moment of inertia from the table is 1/12 ml squared. With this one, I think that's going to make this whole thing 15. So I think it works out to be. But let's make sure it's 1/12. The mass of the rod was 20. Length of the rod is 3 squared. 1/12 ml squared. So 3 squared is 9, 9/12 is 3/4, 3/4 of 20 is 15. So this equals 15 kilograms meters squared. So now you have the 2 points. You have the net torque, that's here. You have the moment of inertia, that's here. All you have to do now is divide a couple things. It's not particularly tough now, but this is the steps that you have to go through to solve one of these problems. It's gonna be 10 divided by 15, so I'm thinking it's about 0.3, maybe a little bit more than that. Oh, 0.6, you're right, 10 divided by 15. So alpha should be about 0.6 radians per second squared. Maybe 0.7. The angle doesn't change too much. Here's what they do on the AP exam. Just so you guys get an idea of how they're going to trick you, and they will. They're going to do this. They're going to give dotted lines like that, and they're going to tell you this angle is 30 degrees. They're going to give you the wrong angle on purpose. And you're supposed to know that they've given you the wrong angle and that you need to use the right angle. So they'll give the angle away from the perpendicular. People will use that. They do it on the multiple choice all the time because they're in a hurry. But all these angles have to be between R and F. That's the angle that they're looking for. All right. I got to see if you remember something. And once you see it, you're going to be unhappy. But I have no choice. This is the next thing. Do you remember these? It might bring up sad memories. Yeah. I can feel you on that one. Way back in October, this is a modified Atwood machine. Do me a quick favor, because you guys are very good. Can you kind of just give me a couple of free body diagrams? Remember, let's say that this is frictionless. And keep in mind, if you were to release this system, would it accelerate? If there's no friction, would it start moving on its own? So keep that in mind when you draw the size of your forces. We have to hurry because there's only a few minutes for the bell rings. So even less. We're going to pick up here, but remember, the downward force would have to be less than the upward force or it wouldn't accelerate. So tomorrow we're going to pick up right here. What I would like you to consider is it's hard to draw a free body diagram for the pulley using the same rules that you've used before. And the reason isn't because you are incapable of doing so. It's because the pulley has forces that act in such a way as to cause it to turn. So where the force acts is actually as important as how big the force is and in what direction it acts. So for the pulley, I draw a circle somewhere away from the object so that you can draw how the forces act on the pulley apart from how they act on like the other objects. So in the case of the pulley, draw the forces where they attach to the object. For example, I drew a tension, so there's probably a tension acting there on the pulley. Can you draw the other forces acting on the pulley? I suspect you should be about done. This doesn't take very long. But in your drawings, look at the pulley. Is the net force on the pulley what you would expect? Did you draw enough forces to deal with the net force on the pulley? If you don't know what I'm asking, does the pulley go anywhere? So, are the forces balanced on the pulley? For every left force, is there a right force? For every up force, is there a down force? Because if the pulley doesn't go anywhere, then the net force on the pulley must be zero. I think it's probably likely that you guys drew two forces on your pulley. One like that and one like that. But that would be a net force that would cause the pulley to go this way, wouldn't it? So there must be something else acting on the pulley to keep it from moving. Which is why I drew this little bracket here. Something to give you a clue as to what I'm trying to talk about here, that there's probably a force this way on the pulley. From the bracket, from the thing that holds it. I'm not even sure what you would call this. I'm going to call it a normal force, for lack of a better term. But it acts at the center because that's where the pulley is mounted. You guys have seen the pulleys in class. You've mounted them to the tracks before. You know what I'm talking about. And some of you have had it break off, which means that whatever was holding it wasn't doing its job. Now, did you draw the weight greater than the tension on this box? So you're demonstrating that the net force must be such that the box will accelerate downwards. Agreed? Let's say that the pulley has inertia, that it's a massive pulley. And I don't mean massive like huge, I mean it just has mass. How does the pulley having mass affect this problem? Aw. Yes, sir?
Well, the system has mass that require more energy and movement, so the flow hanging off the pulley has mass.
I think many of the things you said are right on the money. If the pulley has mass, it's going to take energy to get it to move. It's going to have to take that energy from the boxes. I mean, the boxes won't get as much of the energy that's available because some of it has to go to the pulley, which means the whole system's going to go slower. I think that's an excellent explanation. And by the way, there are two explanations. I think that one's excellent. I would write that down. Because when you're asked on the test, how does having a massive pulley change the outcome? That explanation hits all of the boxes. It talks about the fact that there's a finite amount of energy in the system. That the boxes are going to get some of that energy. But when you add in the pulley, it takes the energy away from the boxes, thus slowing the system down. It hits all the boxes. It's a good, solid, and I think it's a good, solid explanation. I don't think it's the only explanation, though. I think there's two explanations you should know. Because the energy explanation speaks to velocity. I think a force explanation speaks to acceleration. If the pulley has inertia, then by definition, its inertia will make it more difficult for the system to accelerate. Right, that's the definition of inertia. So if the pulley has inertia, the inertia of the system increases, and therefore the system is more difficult to accelerate. Both of those explanations are good. I think you should know both of them. So an argument about energy, great, and an argument about inertia and force, great. It's not like the pulley having mass changes the mass of the box that's hung. So the force on the system stays the same, but there's now more inertia. Now, we've done these problems before. Do you remember doing them first semester? So do you remember that you look at that box on the table and say, well, there's one unbalanced force, and that equals 2ma. Familiar? And you'd say, or hopefully you'd say, well, I want a common direction that I'm going to call positive. And therefore, the box hanging off the table would have mg minus t equals ma. Does that look familiar to y'all? I said y'all. And you might do substitution to find out what the acceleration of the system is. That should be familiar. What I would normally have done is probably write this here, t equals 2ma, and then add those two things together. Remember me doing this kind of stuff first semester? Or doing substitution, one of the two. The t's cancel, and we're left with something like mg equals 2m plus m times a. And I'd say something like, look at that. It looks just like Newton's second law. Net force equals ma. Familiar, I hope. I'm just trying to provide, I read some teacher joke today, provide scaffolding, which is activating your prior knowledge. Teacher jargon is so stupid. I'll remember that during my cognitive development classes. Okay, so I'm going to just back this up a little bit. And I am glad I'm recording all this. If the pulley has inertia, then the tension in the string has to be what causes it to turn. Agreed? Now this part's going to be more challenging. So here's where I really want you to stop being complacent, saying, yeah, we did all this before, Mr. Shelton, no big deal. Because in a few moments when I say I want you to try this on your own, you're all going to just stare at the blank little page and the little blue lines and go, I don't even know where to begin. I don't want that to happen, okay? The only way the pulley accelerates is if there's an unbalanced torque acting on it. It's the only way it accelerates. Once the pulley has inertia, it can only accelerate if there's an unbalanced torque acting on it. And based on what I've drawn, it looks like the torques are balanced. I have a torque from this tension causing it to try and go clockwise, but this tension is the same size and it's trying to get it to go counterclockwise. The pulley wouldn't turn if the two tensions were the same. So I'm here to tell you today, the tensions can't be the same or the pulley can't accelerate. If you introduce a pulley that has mass, it changes the tension on the string. It has to, in order for there to be an unbalanced torque on the pulley. If you add mass to a pulley, the tension is no longer the same. It changes the tension on one side of the pulley. That adds a level of complication here. I'll say it for a third time. If you add mass to your pulleys, because they have inertia, the tension on both sides of your pulleys changes. In this case, T1 is going to have to be greater than T2. The issue, though, is even though the tensions are different, the blocks are still connected by a string. They will still have the same acceleration. So even though there's different tensions now, the acceleration of the two blocks is still going to be the same for each block. So I have to show you how to deal with this. And so far, this part I'm expecting you know. The only thing you have to do now is recognize that these two equations can't be added together because they don't have the same tension in them any longer. So now you have to include the pulley. This is how the pulley's inertia gets worked into the problem, is dealing with the pulley. And because the pulley is not moving, it's spinning, we're dealing with net torque equals I alpha. So, I'm going to just kind of move this, make it a little bit smaller and put it to the side to deal with this part. We've done this problem a couple different times. I'm going to continue to talk about how to do this problem. There are 3 things you have to do. And if you have not yet gotten this as a set of steps in your notes, now would probably be a good time. You have to deal with the sum of the torques. That's one thing you have to do. You have to deal with the inertia of the object. That's another thing you have to do. And then you have to deal with Newton's second law. There are 3 things that have to be done. And I'm going to add a 4th in just a minute. So let's do the parts of this that we are familiar with doing. For example, I see that there are 2 torques acting on the pulley. One from the tension that's of the block that's hanging, and one from the tension on the table. I will call those torque 1 and torque 2. I'm going to set this direction to be positive. That's into the board. That makes the torque from tension 1 positive and the torque from tension 2 negative. Now, look, I'm just pausing for a minute. I am of a belief that you already have in your notes some kind of scaffolding, teacher word, that told you have to check for direction, because that's what we did yesterday and the day before. I'm just building on it a little bit more. So when I say you have to deal with the torques, I'm assuming all these little steps about dealing with the torques are already there. Like recognizing that a torque is made up of 3 things. I don't want to have to say this every single time. Dealing with the torques means you already know to go check those steps and do those things. The nice thing about a pulley is that the torque arm distance is just the radius of the pulley. The other nice thing about a pulley is that the string always comes off at a tangent, which means the angle's always 90 degrees, so this is always 1. For a pulley, you'll never have to worry about the angle. The force, you have to use whatever the force is. In this case, it's T1 for torque 1, and it's T2 for torque 2. And since this is a net torque problem, you're going to be adding them together. All right, so that's step 1, deal with the torques. Step 2, in your notes, I would want you to have a couple things written here. First, dealing with inertia means one of 3 things. Thing number 1, they tell you the inertia. They say it's 4 kilogram meter squared. They give you a value to use. That's probably the easiest if it's a number problem. Number 2, the other way they could make you deal with inertia is to just tell you to use I. So it's possible they will say I can be in your answer, the letter I, and that's all you have from which to work is I. The third thing they can do is they can give you the shape. They can tell you it's a disc, a ball, a sphere. They can give you something. I'm going to give you a shape for this one. So of the 3 possibilities, there is give you the number, tell you to use I, or give you a shape to use. For the examples we're going to do, we're going to use a shape. I'm going to tell you that the pulley is a disc of mass M and radius R, which is what we've been using already. Which means, mass lowercase m, just like everything else. And that means disc. They're telling you to look up the shape from the table. So in those 3 things that you might have to deal with when it comes to moment of inertia, the third one means look it up in the table, or they give it to you. On the exam, they're likely to give you the equation for a disc. But don't be thrown off if they don't. If they just tell you you have a pulley and it has moment of inertia I, okay, just put an I in there. It's pretty easy. So don't be worried if they don't tell you the shape. I have graded a ton of work from the folks in mechanics, and the mistake they often make is the problem will tell them just to leave it as I, and they'll try and put in a disc anyways, because that's what their notes told them to do. So I'm trying to be more proactive with you guys. So if it doesn't tell you the shape, it's either a point mass or you put in I. Something like that. All right, so in this case, we're going to use the disk, which is 1/2 mr squared. And so step 3 means assemble Newton's second law. Assemble means net torque, RT1 minus RT2 equals, put in the moment of inertia, 1/2 mr squared, and then multiply by alpha. All right. I've dealt with the pulley. Now, in our prior problems, we have usually tried to eliminate tension and solve for acceleration. Now, you understand we can't really do that yet because I have linear accelerations and angular accelerations. So this next part, I don't know, put a box in your notes, like make this like big note to get points, or don't forget to do this, or something like this, all right? The reason why they would give you the shape is because of what I'm going to say now. They know how the math works. You don't quite yet. If the string connects the pulley to the 2 masses, then the acceleration here is related to the acceleration here, right? Do you understand that the faster the blocks move, the faster the disc spins? Does that make sense? So the blocks are moving quick, the disc is spinning quick. If the blocks are moving slow, disc is moving slow. We talked about this earlier in the year. We talked about it when we were dealing with kinematics. And you guys hated it, but this next step is critical. You have to do it, and you have to remember to do it. And it's almost always the linchpin. If you can't do this, it can't be done. Kinematics. How do you go from angular to linear? You use one of those. That means substituting in for alpha, A over R. Now, you might not understand why this is important, but it's the only way to bring these three relationships together. But also, please look at what happens. Look at the algebra for a minute. Focus on the torque equation. Do you notice what happens to all of the R's? I can factor out this R, and it cancels one of the R's on this side. And then I can cancel the other R that's remaining with the R that's in the denominator. If they give you the shape and you do this conversion, all the R's should cancel. It's just a factor of the mathematics. And every physics teacher who writes tests knows this. Which leaves you with T1 minus T2 equals 1/2 MA. It leaves you with something that can be used to solve your question. So let's grab these things, bring it all together. So I don't forget that I have my T2 equals 2MA, and my mg minus T1 equals MA. Bring them all together. The torque brings the two tensions together for you. Now, you have a choice on how you do this. You can do substitution, solve for T1 and T2 and plug it into the torque equation. You know I'm not going to do that. I'm going to add them up. I'm going to line them up by equal sign, and I'm going to point out how there's a negative T2 and a positive T2, and a negative T1 and a positive T1. So if I add all of these up, all the tensions cancel. So that's why I like doing it this way. It's just so much neater mathematically. On the right side, they all have an acceleration in them. So that's going to be 1/2 m plus 2m plus m times a. And I know you guys kind of hate this because I say it all the time, but look at what you get at the end of doing all this. You should always get something that looks like Newton's second law. Net force equals inertia times acceleration. The net force was the mass that's hung off the edge of the table. That's what's causing the whole system to move. If there was no mass hanging off the edge of the table, nothing would happen. Inside here, I have something for each object that has inertia. The mass on the table shows up, the mass that's hung shows up, and now the pulley shows up. So if three things have inertia, there should be three things here. All of them share the same acceleration. Again, I don't try to do this to make you feel like, okay, he's saying it again. I'm doing like this, you know you've done it right if each thing with inertia shows up there. You know you've done it right when the internal forces cancel out. That's how you know you chose the right sign for everything, and that's how you know you made sure you kept track of each thing. Because there's a lot to keep track of here. Now, you could solve this for A, but that's just more algebra, and yeah, you could add 1/2 to 2 to 1 and get all those together. That's fine. But what I'd really like to do is kind of show you what my expectations would be for what I think you could do with this information. If I was going to ask you to do something on your own, and we will run out of time here in just a minute, but that doesn't mean I don't think you can get a good start. This is a simplified version of the problem you just saw. So I have a string that I've wrapped around a pulley. So it's not connected to anything but the pulley. Does that make sense? And I've hung a box off of it. The pulley has mass 3m, radius r, and is a disc. The box has mass m. I release the box. Would you agree that the box probably goes downwards? And would you agree that the pulley probably spins? Can we all agree that they probably are related? Can you try this problem? It is identical to what you just did with one less thing to do. It's just a practice to see if you can pull the pieces together. So this one's easier than what you just did. You've done it right when this is what you get at the end. Because the bell's going to interrupt us. And I want to see if you guys can do this. I want to answer some questions. So that's what the answer should look like at the end.